In the previous video, we had a look at a kind of linear recursion, and we found that if the first iterate were chosen between 0 and 1, then all the subsequent iterates would remain between 0 and 1. So there was a kind of stability or trapping property of those sequences and of those matrices that I would like to understand better in this video. So more precisely, the question that I want to at least partially answer is the following. So I'll just do a drawing because it's more intuitive. So if we have a description of a region R, and this we give ourselves, we describe it in some ways, we want to find a set of matrices such that if I take a point X in that region, then Mx remains in that region. So given R, a subset of, let's say, Rn, describe S of R, which is a subset of Rn times n, such that for all m in S of R and x in R, we have mx in R. So this is the stability property that I was mentioning before. And perhaps I should insist on the motivation. So when we're looking at recursions of the shape uk plus 1 is a, let's say, or m here, fit the notations, muk, and let's say x or u0 in R and m u0 in R and m in S of R. This will show by induction that uk is in R for all k greater than 0. And slightly more generally, if we look at recursions uk plus 1 is mk uk and mk is in S of R for all k, then and also nx and u0 is in R, then uk is in R, the region R for all k. So this is the stability property that usually enables us to prove some kind of boundedness or to transfer properties from the first iterate to all their iterates. So if something is true at the beginning, then it remains true along the whole sequence. In this video, I want to particularly focus on 3 examples. And I'll start with the first one here, which is the easiest, which is just the set of non-negative integers or non-negative real numbers. So r plus to the n. So that's just the numbers in Rn, so n numbers, such that xi is non-negative. And we'll characterize S of R in the following way. First is that if m is in S of R, then in particular, m times e1, which is m times 1 and then only zeros, is also in R, the region R, not R. But this is the first column of A. So this will imply that the coefficients of the first column of A all need to be non-negative. So this implies mi1 non-negative. But this applies in fact to all the columns. So applies to all columns. So we infer that mij smaller than 0 for all ij. Conversely, if mij non-negative for all ij, then for all x in R, we have mxi, which is mijxj. Here I'm summing on j, but I'm not writing the sum. This is non-negative, this is non-negative, so this is non-negative. And so this implies that mx is in R. Sorry, I keep writing like this. So this means that we have shown that S of R is, or I should write maybe R plus to the n is R plus to the n times n. So if we want to stabilize the cone here, so this region here where all the entries are non-negative, then we need to take a matrix whose entries themselves are in that region. Now, the second example I want to look at is the example of the previous video, that is the cube. So 0, 1 to the n, which is the x's in Rn such that 0 xi1 for all I. So here this is a subset of the previous set. So because 0, 1 to the n is a subset of R plus n, this first implies that mij has to be positive or non-negative. And now if we take a look at m times the vector 1, 1, 1, so only ones, this will look like the sum of m I1, m 1j for j equals 1 to n, and then sum of mnj for j equals 1 to n. And this has to stay between 0 and 1, in particular smaller than 1. So this implies that the sum of mij is smaller than 1 for j equals 1 to n for all I. So the rows sum to at most 1. Conversely, if mij non-negative and the sum of mij on j is smaller than 1 for all I, then for all x in R, so R here is the cube, we have that mxi is mijxj. This is between 0 and 1. And this is in particular non-negative, so this is going to be smaller than the sum of mij from j equals 1 to n, and this is smaller than 1. So this implies that mx is still in R, and that we found a stabilizing matrix. So in that case, we were still able to characterize that S of the cube is equal to the set of matrices, so m in R plus to the n times n, such that the sum of mij is smaller than 1 for all I. So the sum of the rows is bounded by 1. And in fact, this is exactly what we were looking at in the previous video, because we had matrices of the shape 1 minus alpha alpha, beta 1 minus beta, and this sum to 1, this sums to 1. So we were kind of the boundary of that region, because here we had the equality on every row. And the third example that I want to look at is the probability distributions of size n. So probability distributions of size n. So this is equal to the set of x in Rn, such that xi is non-negative and the sum of xi's is smaller than 1. So in particular, if we take a matrix in S of R, then in particular M stabilizes, then M stabilizes R plus n. So we will have Mij non-negative. And also, if we look at Me1, this is going to be the first column, and it needs to sum to 1. Sorry, this is not smaller or equal to 1, this is equal to 1, because the sum of probabilities sum to 1. So here we need that the first column sums to 1. Sorry, I should write that in. Sums to 1. And this is true for all columns. So all columns sum to 1. Now conversely, if Mij non-negative and Mij, the sum here is on I from 1 to n, is equal to 1 for all j, then for all x in R, we have that the sum of mxi from I equals 1 to n, this is equal to the sum of I equals 1 to n times the sum of j equals 1 to n times mij and then xj. Now we can we can switch these two, and we are able to sum on the rows first, so that sum on the columns first, so that we'll find a 1 here. So this is equal to sum from j equals 1 to n, sum of I equals 1 to n, mij, but now this does not depend on j, xj, but this is equal to 1 here. So this is equal to the sum from j equals 1 to n of xj, which is equal to 1. And so that means that mx is in R. So here again, we've been able to show that S of, let's say, I'll write Pn, the set of probabilities of size n, is the set of matrices M in Rn, R plus n, such that the sum of Mij on I this times is equal to 1 for all j. These matrices are known as stochastic matrices, or more precisely, row-stochastic matrices. And they are important in the theory of Markov chains and of probabilities in general, because they're because of their relation with probability distributions. And the set here is known as the set of sub-column-stochastic matrices. Because here the rows sum to at most 1, so this is why the sub. Yes, and these are also related to probability distributions, but more precisely to convex combinations and to averaging in general, as we saw in the previous video. So I guess that's it for this video. I wanted to show that at least in some cases we can characterize what the matrices that leave a particular set invariant look like. And I'll probably do another video in which, given an arbitrary polytope, so an arbitrary, let's say, n polygons, a polygon in whatever dimension, I characterize what the set of matrices that stabilize that polygon look like. Yeah, thanks for watching.